Okay, gentlemen, this is the Chapter 5 homework number 3, the third homework from Chapter 5, last final homework from Chapter 5. First question is asking how many stereocenters does Taxol have? So I gotta hold my camera manually right now, so sorry for the shakiness. But let's find all our stereocenters and see how many we have. So only sp3 carbons are valid choices here, so I'm not seeing any so far. Here's gonna be my first one. Let me change my pointers. Here's going to be my first one, right? This carbon has 3 different groups that are shown and then also an H, or sorry, this one has 3 different groups that are shown and also a hydrogen attached to it. So 1, this one is also chiral, 2, okay, 3, not this one, because they have too many of the same groups attached, right? This has 2 H's, this has 3 H's. So 1, 2, 3, 4, 5, 6, 7. Um, did I count this one already? I don't remember now. 8. I'm going to say that I didn't. 8. I'm missing one. Missing a couple. 1, 2. Let's just look at all the sp3 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, I got 11 here. Make sure you don't fall for the trap of this CH2 here or this CH2 here. Okay, we're looking for things that have 4 different groups attached to them, sp3 carbons with 4 different attached groups. Okay, let me get this book out of here. Okay, the next one is asking about making, number 57, it asks me if I have a racemic mixture of this molecule. I messed it up. This molecule, so double bond O to the N to there, like this. H OH like this. Okay, so it asks if I have a racemic mixture of this molecule and I try to make a diastereomeric salt, what are the 2 salts that I get? What are my sort of diastereomeric salts that I get as a result of mixing this with a base that is itself chiral? So first we need to figure out where's our chiral carbon. It's going to be this one. Okay, this carbon right here is chiral because it has 4 different groups attached. So that means one enantiomer of just this by itself is going to have this coming towards us, and one enantiomer is going to have this going back. Okay, so I drew those 2 enantiomers. Then we said we're reacting it with a chiral base. So I'm reacting it with this. Basically, this is an NH2 as the base form. Right now we talked about acids and bases more. That's going to deprotonate the carboxylic acid to give me this ammonium derivative. Okay, which is itself chiral because I have a chiral carbon over here. So while really I'm producing enantiomers of my anions, right? These 2 are enantiomers of each other. My cations, which are part of kind of the molecular formula of the salts that are forming, right? This is what my first one looks like. So I have this configuration at this carbon, and the same this fluorine is whatever configuration that the chiral base started as. Okay, so if I look at between these 2. Okay, the other enantiomer is going to form a salt with the chiral base the same way this one did. So now, like I said, the anions are enantiomers of each other, but the cations are not. The cations, these stereocenters are the same. So this is just like any other molecule that has multiple stereocenters in it, right? I want to look at, to figure out if these are enantiomers or diastereomers, I need to look at how many of my chiral centers flipped. If I flip one chiral center but not all of them, that's diastereomers. If I flip all my stereocenters, that gives me an enantiomer. So in order to have an enantiomer of this salt, I would have to also have the inverted stereochemistry at the chiral center on my base. Okay, so this fluorine would have to be going back. I'd have to use a different reagent. So these are diastereomers. Okay, and I think it tells us that, right? It says draw the 2 salts. Okay, we did that. And then we said these are diastereomers, right? Because we only invert one. Looking at the top salt, this entire top salt versus this entire bottom salt, I'm only inverting one carbon and not both chiral carbons. If I invert both, they're enantiomers. But since they're diastereomers, Diastereomers are the ones that have different physical and chemical properties. So one of them might be more soluble than the other one. They might interact with silica in a slightly different way. They might have different boiling points or melting points. These are all things you might be able to exploit to separate them. Okay, because they're not enantiomers. Only enantiomers have the same properties aside from the whole polarized light business. Okay, number 59 says if Taxol, that was the problem, the molecule we did in the first question. It says if Taxol has a minus 49 rotation of minus 49 degrees, then what is the rotation of its enantiomer? Well, if the minus Taxol is minus 49, then the plus Taxol enantiomer must be plus 49. This is as far as we can say. Okay, we can only say that one enantiomer is going to be the same rotation but opposite sign of the other enantiomer. If they're diastereomers, we can't make any kind of prediction about if I know that 49 degrees is Taxol's rotation, or minus 49 degrees is Taxol's rotation, and I have a diastereomer of Taxol, I have no clue what its rotation is going to be. It could be anything. Okay, that was a question on the quiz. You can only say it's the opposite if they're enantiomers. If they're diastereomers, you literally cannot say anything about the rotation. You'd have to do the experiment to figure it out. Because rotation of plane polarized light is not well predicted by a lot of models. Okay, we have to just kind of experimentally find it. Okay, 62 is asking me, what is 62 asking me? It says we have the plus isomer has a rotation of plus 25 degrees. And then we want to know if we get 84% EE of the plus isomer, 84% EE of the plus isomer. If I have 84% EE of the plus isomer, my question is, what is the rotation of this solution? So 84% EE of plus means there's still at least 16% of the minus, but well, I guess that's not exactly what it means, is it? 84% EE of the plus means that at least some of the solution, is what I meant to say, is also the minus. So if it was pure plus, pure the plus enantiomer, pure the plus enantiomer, or the S enantiomer, then it would be plus 25. But we need to figure it out based off this enantiomeric excess. So remember, this excess means only 84% of the solution is actually rotating the light in the plus direction, because the other 16% of the solution is racemic, meaning it's half, or 8% plus and 8% minus isomer. So the part that's not in excess is racemic, meaning they cancel each other out. So only this excess stuff is what's going to rotate the light, right? The minus will rotate it this way, the plus will rotate it this way, and together they're going to cancel each other out. Okay, so these will just say their rotation cancels. So then all I'm really seeing is this 84% of the excess that actually does the rotation. So then if I want to figure out what is the extent of rotation, I just need to take 84% of my maximum rotation value, which was 25 degrees. Okay. And when I do that, I get 21. Let me double check that real fast. Pretty sure that's right. Yeah, punch that in my calculator and I got 21. 21 degrees is our rotation. And it wants to know what's the percentage of the S enantiomer, which was the plus enantiomer, okay, in this problem. The total percentage then, well, I know it's 8% minus, so it must be 92% plus. And I'm calling this plus instead of S because it told us the S enantiomer has the specific rotation in the positive direction. Okay, so 92% plus, which is again the S. S isn't always the plus, okay, and R isn't always the minus. It varies from molecule to molecule. You can't predict based on that alone. Okay, last one. It says something. Oh, it says one amino acid is achiral. There's one amino acid that's not chiral, which is a little bit weird to think about at first blush, maybe. So why is this? Well, here's our general amino acid, right? I have my amine group, I have my carboxylic acid group. I'm showing you the Zwitter ion or the Zwitter ion form of this. That is the neutral form of this amino acid in solution. Okay, and if it's an L amino acid, I have my R group going back like this. Okay, So the question is, which amino acid is achiral? Well, most amino acids are chiral because this carbon right here is chiral, right? And it has 4 different groups around it. 1, 2, 3, 4. But not if the R is a H, right? If my R group is just a hydrogen, this is achiral, and that is exactly the case in glycine, our simplest amino acid. Okay? So that's the end of this homework. Okay, see you on the next one.